Imagine you're watching a video from a single camera, no depth sensors, no stereo vision. Just one frame. Now your task is to reconstruct the full 3D pose of a person, where each joint is in space, how their limbs are positioned, even when they're partially hidden behind an object or turned away from the camera. This isn't science fiction. It's monocular 3D human pose estimation, one of the most challenging problems in computer vision. And it's deeply ill-posed. For every 2D image, there are countless possible 3D configurations that could produce the same projection. Depth is ambiguous. The camera can't tell if a hand is close or far, it just sees a point on the image plane. Traditional approaches try to solve this by predicting a single 3D pose, the most likely one based on a 2D input. But that's dangerous. In complex scenes, like a person bending over or an arm crossing in front of their body, this single estimate can be wildly wrong. Worse, it's overconfident. The model thinks it knows the answer, when in reality it doesn't. That's why the field is shifting toward probabilistic 3D human pose estimation, where instead of guessing one 3D pose, we model a distribution of plausible poses. We acknowledge uncertainty. We say, here are 200 possible ways this person could be standing, and here's how likely each one is. And now, a new method called FMPose is pushing the state of the art, not just in accuracy, but in speed, stability, and generative quality. FMPose is built on a powerful new idea, flow matching with optimal transport. At its core, FMPose learns a continuous transformation, a flow, from a simple source distribution, like a standard Gaussian, to the complex, real-world distribution of plausible 3D human poses. This transformation isn't random. It follows the optimal path, the shortest, most efficient way in probability space, from noise to meaningful structure. This is where optimal transport comes in. Think of it like moving a pile of sand from one shape to another. The optimal transport path tells you exactly how to move each grain, minimizing total effort. In FMPose, that path is a straight line in time, from a random Gaussian sample at time t equals 0 to the true 3D pose at t equals 1. The model learns the velocity field, the direction and speed, that moves every point along that path. And how does it learn that? Through flow matching, a technique from recent AI research that avoids the instability and complexity of older generative models. Compare this to diffusion models, the current trend in generative AI. They work by gradually adding noise to data, then learning to reverse the process. But that's like trying to reconstruct a shattered vase by guessing how each shard was placed. It requires solving a stochastic differential equation, a noisy, unstable process that needs hundreds of steps to generate a single sample. It's slow, fragile, and hard to train. FMPose, on the other hand, uses continuous normalizing flows, a much cleaner framework. Instead of noisy reverse diffusion, it learns a deterministic ordinary differential equation, an ODE, that defines the smooth, continuous evolution of the pose from noise to reality. The neural network predicts the velocity of each joint at every moment, guided by the optimal transport path. And the result? Faster, more accurate, and more stable generation, with far fewer steps. Now, how does FMPose know which 3D pose to generate? It needs a condition, the 2D input. But not just the 2D joints, not just the peak of the heat map. Instead, FMPose uses top K arguments from the 2D heat maps, the most probable locations, but also the second, third, even 10th most likely positions. This gives the model richer, more nuanced information about uncertainty. Then it processes this 2D data using a graph convolutional network, or GCN. The human body is a graph, joints are nodes, connections are edges. But here's the key insight. Instead of fixing the graph structure to the natural skeleton, like elbow connects to wrist, FMPose learns the graph connections during training. The adjacency matrix is initialized to 0, then adaptively optimized. Why? Because real-world poses aren't always anatomically ideal. In a crouched position, the spine might appear more connected to the hips than the shoulders. In a complex motion, joint relationships shift. By learning the connections, FMPose captures these dynamic dependencies and generates better 3D hypotheses. This lifting condition, the GCN output, is then fed into the flow model, which uses it to guide the ODE solver. At inference, we sample from the Gaussian source, and the ODE integrates the velocity field step by step, using a stable second-order Runge-Kutta solver, until we reach the final 3D pose. And because the flow is continuous and smooth, we can generate hundreds of diverse hypotheses, each one a plausible 3D configuration, just by sampling different initial noise vectors. Now let's talk results. On Human 36M, one of the most widely used benchmarks, FMPose outperforms all prior methods, including the current SOTA diffpose. It achieves 41.7 mpjpe, a 2.5 improvement over diffpose, and 30.6 mpjpe, a 1.5 gain. On the ambiguous poses, where joints are occluded or the pose is complex, FMPose improves by 7.6 min mpjpe, showing it excels where others fail. On MPI-INF 3DHP, a challenging dataset with real-world scenes, FMPose achieves 87.9% PCK on indoor green screen scenes, the best result to date, and 84.1% on outdoor scenes, proving strong generalization. And on 3DPW, the most difficult in the wild dataset, FMPose beats all single-frame methods, even outperforming some multi-frame models, with 56.2 mpjpe after fine-tuning. But beyond numbers, the real power is in uncertainty modeling. Look at the qualitative results. When a hand is fully occluded, FMPose doesn't just guess. It generates a wide spread of hypotheses, showing how the hand could be positioned along the optical axis. The model doesn't pretend to know. It shows what it doesn't know. And when the 2D detector fails, when the camera is blurry, or the person is in shadow, FMPose still produces plausible upright poses. Why? Because the flow is trained to push toward the true distribution, not just the noisy input. Now let's talk efficiency. diffpose, a leading diffusion-based method, has 11.5 million parameters and requires 32 denoising steps, slow and memory-heavy. FMPose, just 4.5 million parameters, 60% smaller, and only 25 ODE steps. Even at 5 steps, it's 43% faster than diffpose, with competitive accuracy. And the ODE solver? We tested multiple variants. Second-order Runge-Kutta RK2 strikes the perfect balance. 36 ms per 200 hypotheses, 28 fps, fast enough for real-time applications. What's more, ablation studies confirm every component matters. Removing the GCN drops performance by over 2. Skipping the top K arguments hurts accuracy by nearly 5%. And learning the adjacency matrix, rather than fixing it, improves results by 0.8. So why does this work so well? Because FMPose combines 3 powerful ideas. Optimal transport for a stable, straight path in probability space. Continuous normalizing flows for smooth, deterministic generation. Learnable graph structures for dynamic, context-aware 2D to 3D lifting. And the result? A model that's not just more accurate, but more reliable. More aware of its own uncertainty. More useful for downstream tasks, like robotics, autonomous driving, or augmented reality, where knowing how uncertain you are is just as important as knowing what the answer is. FMPose isn't just a new state-of-the-art. It's a new paradigm, one that trades the fragility of diffusion for the elegance of optimal transport, and the rigidity of fixed graphs for the adaptability of learned ones. And as we move toward AI systems that need to reason under uncertainty, not just predict, methods like FMPose will be essential. Because in the real world, certainty is rare. But clarity, even in uncertainty, is possible. And that's what FMPose delivers.